Okay, so hello everybody. My name is Professor Jaroslav Katon. I'm coming from University of Novi Sad in Serbia, and I will talk today about biopolymers obtained by food waste valorization. So this lecture is a part of Erasmus Plus program funded by the European Union. The project is entitled Agri-food Waste Management for Sustainable Bioeconomy through Higher Education Curricula and Upskilling. So the project has several goals. Acronym AGRIMA aims for foster universities' capacity building for the green transition through innovation practice and higher education curricula, updating in agri-food waste management for the circular bioeconomy. So AGRIMA tries to address, firstly, advancing pedagogical methods for industrial agri-food waste valorization based on business academia synergies, and second, integrating citizen science in bioeconomy enhanced waste valorization as a means of civic engagement and environmental advocacy. The project is carried out by 6 partners from Portugal, France, Serbia, and Greece. Okay, so this is a short introduction about the project. The outline of today's lecture is as follows. So I will shortly present my team here in Novi Sad, what we are doing here, and so then we'll give a few words about agri-food waste valorization, talk a bit about biopolymers, and then we'll give 2 examples how we can valorize agri-food waste. So let's start. So this is me. These are my coordinates in case you have an urge to contact me. So here is my email address. There is also a web page of our group, so you can find more information there. So basically, as I already mentioned, so the group is coming from University of Novi Sad. More precisely, this is Faculty of Technology in Novi Sad in Serbia. University of Novi Sad, I don't know, have you ever had the opportunity to come here to visit us? So we are quite large university, so there are around 50,000 students attending lectures at 14 faculties from all science disciplines, from, I don't know, law and medicine until technical sciences and technologies. So at the university, we have around 5,000 employees. I'm one of these 5,000 employees. We have a very nice campus here on the bank of Danube River. Large majority of the faculties are situated in this beautiful campus. So I really hope that you will have opportunity to come here and visit us in Novi Sad. So one of these 14 faculties is Faculty of Technology. Just a few words about, so I'm coming from Faculty of Technology in Novi Sad. So we were founded in 1959, so that's 60 years ago. We enroll, we have around 1,400 students at all 3 study levels, bachelor, master, and PhD. We have around 240 employees. And out of this, around 150 is research staff. We are very proud to be, we like to say, the best scientific faculty at the University of Novi Sad. So we have largest number of scientific publications written per researcher as at whole University of Novi Sad. So yeah, this is the faculty, and this is the group. So I'm heading. So the group is colloid chemistry research group. You can find again more details in the web page presented here. We are quite young, so we have two members who, Sandra and Liana, who recently obtained PhD a couple of years ago. We have three PhD students at the moment, Jelena, Neira, and Daniela, and we have Slobodan, who is our guy for taking care of our laboratories. So what we do, so we are, I don't know how much you are familiar with colloid and interface science, but we are aiming to design what we call functional colloids. So when I talk about colloids, so this would be either particles which are larger than molecules, but still smaller than our eyes can see, or we can think of also large molecules, so molecules with, let's say, molecular weight higher than 10,000. So these are also then, when in solution, they will have these colloidal dimensions. We are interested in several applications. So these are food science materials, obtained by agri-food waste valorization. So that is one topic. Then nano and microencapsulations. We are active in sensors for different applications. And we have also wealth of experience in synthesizing and formulating different functional printing materials. And also, our expertise also covers free surface flows, such as drop formation during inkjet printing process. So these are applications. When it comes to expertise, I will just give you some keywords here. So these are colloid and interface science. Obviously, as we today are talking about biopolymers, so one of the expertise is biopolymers. Recently, we are especially interested in biopolymers which are, let's say, weakly soluble or insoluble in water. And then we like to prepare some biopolymer nanoparticles and to use these nanoparticles to produce biopolymer films. Okay, so these films then can be applied in various applications such as packaging, sensors, and so on. Another keyword would be polymer surfactant interaction. So we actually understand very well how polymers behave when they are dissolved, so when they are in solution, and how they interact with different components present in the solution. So these might be surfactants, but also these might be other polymers. It can be ions, they can be maybe particles, etc., etc. Also, we are active in emulsions and dispersions, rheology, and formulation. So quite a lot. But basically, all this is linked horizontally with colloid and interface science, which is our actually expertise. We have, I'd like to say, strong track record in industrial partnerships. So we collaborate with many local industries, but also with some of the leading European companies such as Agfa or Capsugel in various domains. So we try to apply the theoretical knowledge into real life problems. Okay, and we think we are quite successful there. Okay, So this was the, let's say, the introduction part, and let us now dive into the topic of today's lecture, and that is related by agri-food waste valorization, and especially how we can obtain some useful biopolymers out of this agri-food waste. So agri-food sector, as you may already heard, so it's a huge sector. I don't know if you ever uh, uh, was thinking about this, but it's really, it has a massive socio-economic, but also environmental footprint. So it really influences to a large degree our societies in a number of ways. So it's already big today in this agri-food sector, but what is known, so it is expected to grow even further in the coming years. This is mostly because we have this increasing human population. So more human population, so you will need to provide food for all these people. So that's why you have to intensify even more this agri-food sector. So that's one reason, and the second reason is that not only we have more and more people at our planet Earth, but these people are having every year better and better standard of living. So that's normal. So people wants to live better, and on average, standard of living is increasing globally. This is important because the higher the standard of living, the more food we actually consume. So we buy, but we also increase the waste from food we buy and produce. Okay, so that's the second thing. So as we have these let's say issues of growing human population and of increased standard of living. So of course there are many ways that people are trying to intensify this agri-food sector, so to produce a kind of intensive but sustainable agri-food industry. So sustainability is more and more a word that we are, let's say, in the focus of everything we actually do. So also in this agri-food sector. So there are many, let's say, smart solutions and smart approaches how we can tackle this grand challenge of 21st century. I listed here a few, so such as precision agriculture, smart farming, circular economy, and so on. So what I already mentioned is that developed societies, so the more societies are developed, so the more they are inefficient in their use of food. So especially for developed societies such as European countries or the States, and now China more and more. So we are all notorious for our inefficient use of food. So you can think of your own example. So if you buy from a grocery, for example, fresh vegetables and fresh fruits, eventually you will throw away maybe, let's say 20, 30, on average, it's around 40 even percent. So that's very, very inefficient use. That's something that we cannot, we are not proud of. So when it comes to agri-food waste, so here are some numbers. Around 20% of all food that we produce currently in Europe is eventually wasted. Okay, so that's on average. But if you, for example, pick only fresh fruits and vegetables, then this percent increases even to up to 40%. So almost half of everything we produce, we eventually throw away as a waste. So that's really, really uneconomical management. Another aspect of this, because modern agriculture involves for sure watering of crops, and actually around 80% of all fresh water that we as humans are spending is used actually on crops watering. So not only that we throw away the food we produce, we at the same time throw away actually the water that we use for producing that food. So that's also another aspect which is, of course, unacceptable. So this is, of course, recognized as a burning issue of our century, and there are many documents which try to, let's say, put an emphasis on this challenge. One of the let's say the global document is United Nations 2030 agenda, especially 12.3 Sustainable and Development Goals, which targets to halve per capita food waste at the retail and consumer level by 2030. Okay, so European Union has aligned with this agenda. So we have our European Green Deal, and within this Green Deal there is farm to fork strategy, which targets especially food loss and waste prevention as one of the four main strategy pillars. So, okay, so there is a policy that identifies the issues, and of course, then we are trying to, let's say, work on this policy even through the project such as this Erasmus Plus project. So, okay, so we waste food too much. So there are then, of course, many approaches. So how you can either reduce waste or maybe to somehow valorize the waste, or maybe to improve the management in the food chain supply. So there are many ways how you can, let's say, contribute to this European Green Deal policy. One of the ways is to try to give some added value to our food. Okay, so to try to high value valorize our agri-food waste. So today, agri-food waste is either wasted, or it is maybe transformed to some animal feed, or maybe for let's say increase the fertile of our lands. Okay, so that's the common use. But of course, there are many efforts to try to add value to this agri-food waste. I listed here some examples. So, of course, you may imagine that this agri-food waste is enormously rich in all kinds of valuable biomaterials. So I listed here just a few examples. So, for example, some flavonoids or essential oils from citrus peels can be used in, let's say, functional food or nutraceuticals. Oil from avocado seeds are often found today in cosmetic and personal care products. For example, starch from potato peels can be used for biodegradable packaging, and so on and so on. So there are, let's say, many smart approaches how we can extract some materials from agri-food waste and then reuse them in some added value applications. So this talk is in line with this, let's say, direction, where we are focused mostly on isolating and extracting biopolymer materials from agri-food waste. So let me just spend a few minutes about to say a few words about biopolymers. I don't know what is your background, but okay, polymers or biopolymers, as we call them, so these would be actually natural polymers, or as we also often call them, macromolecules, which are essentially synthesized by cells of all kinds of living organisms, okay? So you know that you have some monomeric units, so let it be these green dots, and during this biosynthesis in the cells of living organisms, so these monomeric units will be linked to form a macromolecular chain. Okay, so this chain, as you can see, is much larger than, let's say, molecules of solvent. This can be, for example, water molecule, while solvent molecules, so these light green dots, are of comparable size with monomer molecules of our macromolecule or our biopolymer. Okay, so there are different kinds of these biopolymers. So if these monomeric units are nucleotides, then the biopolymer would be polynucleotide. Okay, so these would be, for example, DNA macromolecule. If these monomers are, well, let's say, simple sugars or saccharides, so then you, by polymerizing, you obtain polysaccharide as biopolymer. If these green dots are amines and you link the amines with peptide bond, you obtain actually polypeptides. Okay, so these are actually proteins. So they are also, there is some storm coming here. There are also some other types of not so common, such as polyesters. Out of these biopolymers, industrially most important are for sure polysaccharides and polypeptides or proteins. Okay. I would like to say also a couple of words about the relation between biopolymers and solvents. Okay, so if you put biopolymer into a solvent, then there will be a kind of equilibrium between this biopolymer chain and the solvent molecules. Okay, so and there are basically three colloidal states when biopolymers are in equilibrium with solvent molecules. So first, that's a solution. Okay, so you dissolve, for example, some starch in water, and the water molecules will bind to the starch molecules and contribute to dissolution of this biopolymer. So that's one example. Then the second example would be gels. Okay, so gels are already some, let's say, specific colloidal structure, and even more specific. I don't know if you heard of. So these are coacervates. Okay, so when you look at these three colloidal states, then macromolecules in solutions will have the most pronounced interaction of solvent molecules and these biopolymer chains. the biopolymer chain will be, as we say, well hydrated or well solvated, and it will have some largest dimensions in the solution. In gels, the dimensions usually decreases, and in coacervates decreases even further. So in solutions, when we talk about biopolymers, so most of them will be soluble in water. So when in water, so these polymer chains will be well hydrated, and as I mentioned, expanded. So basically, for example, if this dotted line represents a polymer chain, usually we will define the sphere which actually represents the size of the polymer. I will not go into the details, so there is many more to say here, but you can imagine that you can represent a polymer chain with one sphere. What is also specific is that some biopolymers will not be soluble in water. So you know that cellulose is the most abundant biopolymer in nature, and it is not soluble in water. So there are also some proteins such as prolamins, which are not soluble in water, or caoutchouc, which is not also natural rubber, which is also not soluble in water. What is also specific about the biopolymers is that depending on the quality of the solvent, these biopolymers can occupy larger or smaller spheres. Okay, so depending on the interaction between solvent molecules and biopolymer chains, this hydration will make polymer chains to expand or to, let's say, collapse. So if the solvent is not that good, so then the chain will collapse, and the dimensions of sphere will decrease. Okay, so that's for solutions. When we go to gels, so gels can be formed when concentration of biopolymer in solution is sufficiently high. So if you have dilute solutions, so when there is actually almost no interaction between neighboring biopolymers, so there is no possibility to form gels. However, when the concentration of biopolymers is higher than what we call critical overlap concentration, and that is the concentration when actually different biopolymer chains start to interact with each other. What happens is that the biopolymers will entangle, okay, so they will interpenetrate into one's and another's spheres, and then these biopolymer chains can form some kind of bonds, okay, so these bonds can be just some physical bonds, but can be also real chemical bonds such as covalent bond or some ionic bond. So in these cases, so if we have bonds between different polymer chains, so this is represented by these dark green dots, then you actually form a kind of network. So that's a polymer network that we call gel. Okay, I'm sure you are familiar with many gels. For example, here it's represented hair gel. This is a gel on the top of one cake. In diapers, you have some super absorbents, which are also gels and so on. So there are many examples. So that would be the second type of colloidal state where biopolymers are in equilibrium with solvent molecules. And the third state is what we call coacervates. Okay, so coacervates are something like liquid or gel-like precipitates. Okay, so this is when the molecules are not anymore dissolved in the solution, but they still contains quite a lot of solvent molecules bound to its polymer chains. Okay, so here this is a image from an optical microscope. So these spheres here are actually oil droplets, and this bluish field is actually a coacervate. Okay, so that's actually a bunch of polymer molecules with some also bound water. So this is let's say coacervate. So there are many ways how you can prepare coacervates. I will not talk about this today. For example, if you dry this kind of emulsions, so you obtain the image on the right side. So these are actually microcapsules of some oil, essential oils. Okay, so then you obtain actually oil in a powder form, which is embedded in the matrix of biopolymer. Okay. Just to finish this section with once again with this precipitation of biopolymers. So what is the difference? For example, if you have some small molecules such as sucrose, for example, or I don't know, ethanol or whatsoever. So the size of these molecules is always the same. Okay, so you cannot change the size of the, I don't know, lactic acid molecule. It's always the same. However, when we talk about the size of biopolymer molecules, so this size can be larger or smaller depending whether it is dissolved in a good solvent or in a bad solvent. For example, if we take, for example, gelatin, so it's a common protein. It's well soluble in water. So in water, it will be its chains. Its chain will be expanded. Okay, the chain will be hydrated. It will be swelled, and it will occupy large volume. However, if you add some kind of non-solvent into this solution, so for example, for gelatin, it could be ethanol. Okay, so if you add some portion of ethanol, then the hydration of the molecule will be smaller, and the size of the polymer chain will shrink. Okay, so it will collapse. If you add even more ethanol, so eventually the polymer molecules, polymer chains will be practically dissolvated, and it will be grouped to form solid particles. Okay, so then we say it's the polymer precipitated and yeah, formed some kind of solid particles. So it's important just to have this in mind that by changing the quality of the solvent, so we can influence the size, but also colloidal state of macromolecules. Okay, so let's go to see some examples. So how we can use agri-food waste to obtain some valuable biopolymers. So first example deals with oil cake, which remains after extracting oil from pumpkin seeds. Okay, so let's have a look. So pumpkin or cucurbita pepo in Latin words. You know, I hope you know this this plant. It is used, for example, to obtain pumpkin seeds, which can be consumed as such or can be most oftenly cold pressed to produce pumpkin seed oil. So if you use this cold press to produce oil, so you obtain oil as a final product, but you are left with the cake, which remains after the oil extraction. This cake so is in composition, it's around 65% protein. So there are huge percentage of proteins. Today, it is mostly used as animal feed. And we were asking, are there any options for some high-value valorization of these proteins which remain in the cake? And we were especially interested in investigating whether these proteins have some colloidal functionality, okay? So these are proteins, and we were asking, okay, so whether they are able to absorb at oil-water interfaces, how well are they in doing so, and can we use them if they absorb at the interface as emulsifying agents? Okay, so in emulsion science, so there is also a trend to replace the synthetic emulsifiers with natural alternatives, and this was, let's say, on this track. Okay, to see if we can use proteins obtained or extracted from pumpkin seeds oil cake as emulsifying agents. So let's see how the research looked like. So on this left part of the slide, so we start with oil cake. Then we do what we call alkali extraction of proteins. So it has several steps. So you defat the cake with hexane. Then you to remove waxes and remaining fats. Then you dissolve at pH 10. So it's alkaline solution to dissolve proteins. What's not dissolved, so you will filter out. And then the dissolved part or the filtrate, you adjust pH to 5 to precipitate proteins. Okay, so proteins at this pH will go out of solution, and you will obtain a sediment, which you can then dry and then maybe grind, and you obtain what we call pumpkin seed protein isolate, PSPI. Okay, so that's one type of proteins that we can obtain from the oil cake. So in these isolates, so there is more than 90% of proteins. Then what we did is to try to enzymatically modify these pumpkin seed proteins. So we used two types of enzymes, so that's alkalis and pepsin. And after enzymatic hydrolysis with these two enzymes, so we obtain what we call hydrolysates. Okay, so pumpkin seed protein hydrolysates, H1 and H2. So in principle, what you do by hydrolysis, you can see on this left image. I don't know if you ever have a chance to look at this kind of image. So this is image obtained after gel electrophoresis, which indicates the molecular weight distribution in different proteins. Okay, so you have isolate and you have the two hydrolysides. So you can see that the isolate proteins, so they have several, let's say, fractions of proteins there. So around 36 kilodaltons and around 24 kilodaltons, and then smaller size, smaller molecular weight around, let's say, 14 kilodaltons. If you look at the H1, so that's the after treatment with alkalis, you see remaining the large molecular weight fraction. The middle is also here, but you can see that there is much more, so much darker spot in lower molecular weight. So this is what the enzymes do to, let's say, native proteins. Okay, so it will, let's say, cleavage some bonds, and it will produce some smaller molecular weight fractions. On the other hand, if you look at the H2 hydrolysate, so that's obtained by enzymatic treatment with pepside, you can see that there is not any more high nor middle molecular weight fractions, but only small molecular weight fractions. So everything was, let's say, the large molecules were broken up to create smaller ones chains. So what we obtained, for example, so if we investigate solubility of these 3 types of proteins as a function of pH. So for isolate proteins, you can see that the solubility is quite low, and the minimum in solubility is around 4 or 5 pH. However, if you look at the H1, you can see that the solubility at all pH is actually improved. And if you look at H2 protein, then you can see that solubility is increased even further. Okay, so that's one of the, let's say, aspects of what enzymatic treatment can do to the proteins. Okay, you have now 3 proteins with different solubility and different pH. Okay. At the bottom image, so there is influence of pH on theta potential of the 3 proteins, or the charge of the proteins. Okay, so you can see that at low pH, the proteins will be positively charged. If you go to higher pH, the proteins will become negatively charged. Again, the charge will depend on the protein type. Okay, so by enzymatic treatment, you can influence not only solubility, but also the charge of proteins at different pH. Okay, then we investigated absorption at fluid interfaces, and basically, we can see that the also isolates and hydrolysates will adsorb at the interface. Of course, the higher the concentration of the protein in the solution, the more of the polymer chains will adsorb at the interface. Okay, I will not go into the details. Not only that they adsorb it to the interface, but also then these adsorption layers will have some, let's say, viscoelastic properties. which are important for stabilization of emulsions. And finally, with these three types of proteins, so we tried to prepare some emulsions of, I think, sunflower oil in water, and we were able to prepare the emulsions. Of course, different proteins behave differently in at different pH. For example, at pH 3, the best was H2, so it produced the smallest particle size. At pH 5, the best performance was H1, and at pH 8, yeah, the best. So the alkaline conditions, the best is isolate and H1. If you change the emulsifying conditions, so if you increase concentration of proteins in solution, if you increase the intensity of emulsification process, so you are able then to produce, let's say, typical emulsions with typical micron size droplets, so around, let's say, 3 micrometers, which is, let's say, typical for some food emulsions such as mayonnaise, or for some, let's say, personal care products emulsions such as hand cream. Okay, so this was, let's say, one approach that shows that we can actually use these proteins not only as animal feed, but also to give some added value to this product. The second example deals with zein. That's a corn protein, and this is actually a byproduct of starch production. Okay, so zein is a main storage protein in corn. There are different kinds of zein, alpha, beta, gamma, delta, but around 80%, I think, is alpha zein. So as I mentioned, it's a byproduct of industrial starch production. And what's typical for zein, so it's a protein also, a prolamine, that it is insoluble in water. Okay, so it does not dissolve in water. However, it does dissolve in ethanol water mixtures. Okay, when there is a sufficient amount of ethanol that is more than 60%. So if you have this kind of insoluble protein, so then you can think that this protein can be used to prepare some films, coatings, some packaging, which will have some barrier properties towards, for example, water vapors, humidity, oxygen, and so on. Okay, so that was one of the reasons why we were interested in dealing with zein. We also used some combinations of natural resins, such as shellac and rosin, since they are also soluble in ethanol and also in ethanol water mixtures. So at the graph here, so that's again the charge of zein protein depending on pH. So you can see that again at low pH, the protein will be positively charged. At higher pH, protein will be negatively charged. The isoelectric point for zein is around 6. So it means that at pH 6, the zein is essentially uncharged. So what we do with zein, so we wanted to prepare nanoparticles, okay? So how we prepare nanoparticles from zein? So we simply dissolved zein in ethanol water mixtures, and then we added this solution into a large amount of water, okay? Since water is non-solvent for zein, and ethanol and water are, of course, mixable. So when you put this zein solution into the large amount of water, what essentially happens, So these Zane molecules, so these red curves represents chains of Zane molecules. So when they are found in a non-solvent, so they will just phase separate, okay? So they will merge together and they will form Zane nanoparticle. Okay. And this process is actually very well controlled. So by tuning the processing conditions, so we were able to design the size of the Zane nanoparticles at our will. So from, let's say, 80 nanometers up to some 200 nanometers. So just by changing the conditions of the process. Okay, so in a similar way, we were able to prepare composite nanoparticles, which are composed of Zane and natural resins, okay? The principle is the same, just we dissolve Zane in aqueous ethanol, and we also, in the very same solution, we dissolve some natural resin, so that's these green curves. And again, if you put this large drop of solution into a large amount of non-solvent, which is water here, so the same process happens. So these molecules become insoluble in water, and then they will again merge to form now composite Zane natural resin nanoparticles. So you can see these red lines represents the Zane molecules, and the green dots will be then the resin molecules. Okay, so why we wanted to combine Zane with natural resins? It's because the solubility of these kind of composite nanoparticles can be actually tuned the solubility in water of different pH. So depending on the proportion of Zane or natural resin, so this solubility will change. And we were especially interested in obtaining particles which are soluble at pH, let's say 7 or higher than 7. Okay, why is that important? Because as you may know, in our gastrointestinal tract, the pH changes from our mouth, where it's around, let's say 5. In stomach, it's around 1. If you are very hungry, if you have just had your lunch, then it's around 5. And then if you go to small intestine, so it will increase to, let's say 6, 7. And at the end of the intestinal tract, so in the colon, there will be pH 8. Okay, so if we prepare such kind of particles which are insoluble at pH lower than 8, but are soluble at pH 7, 8, then we can actually use this particle to deliver some active materials to the colon. Okay, so that's like a targeted drug delivery. Okay, and as you can see on this image, so at a certain fraction of resin, Zane and resin, you can see that these small glasses becomes transparent, which means that all composite particles are actually now dissolved. Okay. Let me just see. Okay, I will go back. So by preparing composite nanoparticles, then you can tune the solubility, for example, of these particles, and then you can tune the place of delivery in the gastrointestinal tract. Okay. What you can also do with this particle is to, for example, at low pH, these particles are positively charged, okay? And if you add some polyanions, so some negatively charged biopolymers, such as gamma arabic, then what happens is that these polyanions absorbed electrostatically at the surface of positively charged Zane nanoparticles or composite Zane resin nanoparticles. And you can see, for example, this is again the charge graph. So if you have, let's say, Zane nanoparticles or Zane resin composite nanoparticles, so at the pH tested, so the charge is above 0, so it means they are positively charged. But once you add gamma arabic, the particles becomes negatively charged, as indicated by negative value of zeta potential. And there are other ways to prove the absorption of gamma arabic to surface of Zane nanoparticles, but I will skip this slide. And we'll continue, maybe just to mention, so why we do this is because then you can, when you put the charge, for example, at pH 5.5, this positive charge was very small, meaning that these particles were electrostatically unstable, so they tend to aggregate, okay? But if you add this corona of gamma arabic, so then you increase, let's say, in absolute values, the charge to, let's say, minus 30, minus 40 millivolts. Okay, so in this way, the particles will become more and more stable. So let me just show you one example. So I mentioned, so okay, you can prepare Zane nanoparticles, you can prepare composite Zane resin nanoparticles, but you can also add some active materials, okay? So some materials which have some biological activity or pharmaceutical activity. In this case, we added this as marked by yellow color here. This represents carvacrol, okay? And then you can see the encapsulation efficiency was quite high. So in principle, around 80–90%, so which is very well. And then there is also some, let's say, the release curve of these particles in time. So if we have carvacrol encapsulated in these nanocapsules, I will go a few slides back. It means that these particles will not be soluble at pH lower than, let's say, 7. And then when it comes to at pH 7, 8, so it means when the particle reaches the last part of our intestinal tract, so that's a column, it will become soluble. So the particle will actually, the molecules will dissolve and the carvacrol will be released, okay? By releasing carvacrol, then you can treat maybe some pathogen microorganisms that are inhabiting your column. So that's targeted delivery. And finally, I would like also to mention, so we can also use these particles not only for nanoencapsulation, but we can also use them for preparation of different films, okay, so biopolymer films. So, for example, if you have a fresh strawberry, for example, or banana, or I don't know, apple, if you coat this fruit with some biopolymer layer, which has no smell, which has no taste, which is invisible, so it's transparent, and which possess certain barrier properties, then you can use these coatings actually to prolong the shelf life of fresh fruits, because you will decrease the metabolism of the fruit. So you will increase CO2 levels, so you will decrease metabolism, and that in that way you will actually increase the shelf life of that fruit, and that means that there is a higher likelihood that somebody will eat that food, okay, that it not be wasted. So how we prepare these films? So this is so-called pseudo-latex technology. So if you have a substrate, for example, and on top of the substrate you spray or you put some dispersion of Zane nanoparticles, and you allow this water to evaporate, so you will concentrate the Zane nanoparticles. And since they are plastic, okay, so they will actually merge, okay? They will merge. We say it, in colloid chemistry that they coalesce, and they will form actually one barrier film, okay? So you can see image of this is let's say Zane films obtained by these pseudo-latex technologies, okay? So this is also a very, let's say, promising way of producing edible films, because you obtain a film which is water insoluble, and you do not use actually any organic solvents in this process, okay? So that's a good advantage. Then you can prepare this film out of Zane nanoparticles of different sizes, for example, 90 nanometers or double the size. This is IFM image of the top surface of the films. You can see that the morphology of the films differs depending on the size of Zane particles you use, so you can tune barrier properties of Zane films in that way, and so on and so on. And if you use for preparation of these films composite Zane resin nanoparticles with incorporated carvacrol, then you obtain immediately films which have some antimicrobial properties, okay? So that's, let's say, also one of the applications. And with this, I would like to thank you for your attention, and I hope you enjoyed the lectures from this Erasmus project, okay? Until some next time, I wish you all the best, and yeah, bye-bye.